These are the notes for AP Calculus on the topic of Taylor polynomials, approximation, and remainder error for alternating series. So let's start with talking about a Taylor polynomial. Very much like a infinite Taylor series, except a Taylor polynomial has a degree n, and remember degree refers to the highest exponent of a polynomial. In this case, notice the pattern follows the same as the Taylor series. So sometimes it'll be written as t for Taylor polynomial, sub n for the degree of x equals, this is the original function, or the zeroth derivative, times, if it's x equals a, that would be x minus a to the 0 on this first term. But we don't see that because that's just equal to 1 divided by 0 factorial, which we also don't see because that's equal to 1. And then it's the first derivative, x minus a to the first over 1 factorial, which is also 1, so we don't need to write that. Following the same pattern, the second derivative, a, x minus a squared over 2 factorial, and so on. But unlike the Taylor series, which is infinite, that goes on forever, notice we don't see a plus dot dot dot. So it ends right here. Okay? Actually, I should point to, it's the same n value, but really the degree refers to the highest exponent right there. So this is actually finite, a Taylor polynomial. There's no plus dot 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 at the end here. That shows it goes on forever. So we can use these Taylor polynomials to approximate the Taylor series. And the way we do that is by looking at a specific degree. And even if we don't use an infinite number of terms, it can still give us a very good approximation of a function. All right, so we'll come back to this remainder error for alternating series when we are asked about that concept. So let's take a look at the first example. Again, remember these are the ones we're going to be modifying. The Taylor series you want to make sure you memorize for the AP exam. So this first example says the function f has derivatives of all orders, so f, and f of x equals sine x minus x over x squared. And it says use the fifth degree Taylor polynomial about x equals 0, so it's really Maclaurin also, because it's about x equals 0, to estimate the value of f of 1. But we'll talk about that next. Let's first figure out how we can get the fifth degree Taylor polynomial. All right, so this is like sine, except we're subtracting x and dividing by x squared. So we can say, I'll just call it capital T sub 5 to the fifth degree Taylor polynomial of x. All right, so sine x, we just have to memorize it from the previous slide. Remember, the way you can remember it is sine is an odd function. It's symmetrical about the origin. So in its series, it has all the odd exponents, starting with x to the first over 1 factorial, which we don't need. And then it's alternating, so it's minus the next odd exponent, x to the third over 3 factorial, and alternating, so because the sign graph switches from positive to negative, so plus the next odd exponent, x to the fifth over 5 factorial. So if we were just find the fifth degree Taylor polynomial for just sine of x right here, that would be it. We'd stop right there because it's a fifth degree, that's the highest exponent. However, we have to look at this whole thing to see what's going to happen. Well, notice we've got this minus x here, which you can see is going to cancel out this x. Well, the degree would still be 5, so that would still be the same thing. However, it's also divided by x squared. So because this whole thing is divided by x squared, notice that's going to change this x to the fifth to be x cubed when we simplify it. And then it will no longer be a fifth degree Taylor polynomial. So because of that, we actually have to extend this a little further. And the next term after positive x to the fifth over 5 factorial would be alternating, so it would be negative x to the seventh over 7 factorial. And then notice when you divide x to the seventh by x squared, that's what's going to give us x to the fifth leaving us with our fifth degree Taylor polynomial. And then I'll put the minus x here. So this does go on forever, but we're not going to see that rest of it. So this whole thing right here is sine. And then we can just simplify it. You can see the x and then the minus x, those reduce out, so those cancel out, those are gone. And then if we divide all these by x squared, we subtract the exponents. So our fifth degree Taylor polynomial, write t sub 5 of x, would be negative x cubed divided by x squared. Subtract the exponent, just gives you x to the first over 3 factorial, plus x to the fifth divided by x squared is x cubed over 5 factorial, minus x to the seventh over x squared, x to the fifth over 7 factorial. And since it's a polynomial, we just stop right there. It does not go off to infinity, like our series would. Notice that's the fifth degree Taylor polynomial, so that's the first thing we have to find. Next, we want to use this to estimate the value of f of 1. So the actual value of f of 1 would be, if we plugged in 1 for x for the infinite Taylor series, but we're just using the Taylor polynomial, so we're just going to substitute in 1 for x here. So that'd be negative 1 over 3 factorial plus 1 cubed over 5 factorial minus 1 to the fifth over 7 factorial. So let's see what that gives us. So that'd be 3 factorial is 3 times 2, so that'd be negative 1/6 plus 1 cubed is 1 over 5 factorial, 5 times 4 times 3 times 2 times 1. So that'd be 20 times 6, so 120. Minus 1 to the fifth is 1 over 7 factorial is 120 from the 5 factorial times 7 times 6, which is 42. So 40 times 120, well, 4 times 12 is 48. And then we'd have 2 zeros from the 40 and the 120. And then 2 times 120 is 240. Add those up, gives you 5,040. Now we could get a common denominator here to see what that is, or we could leave it in that form since our common number is pretty large here. So that would be our approximation for f of 1. Now let's see how good our approximation is. Okay? So let's look at our graphing calculator here really quick and see if this is a decent approximation for our function or not. All right, so if I just type this in, negative 1/6 plus 1 divided by 120 minus 1 divided by 5,040. You get that decimal, or if we convert it to a fraction, if we had gotten the common number, we would have gotten, whoops, I made a mistake here, that should be plus. Sorry about that. So, oops, second, actually let me fix that here. Okay, so I forgot to put a plus on the 1 over, as a positive 1 over 120. So now let's try it. Okay, and now let's change it to a fraction. So if we had gotten the common denominator, it would have been negative 799 over 5,040. That's what this equals. Now, and this is what it is as a decimal, let's see how good of an approximation that is. So let's find, if we plugged in 1 into the actual function. Now, these are obviously going to be on the without calculator part of the test, because otherwise there'd be no point in estimating it if you could just punch it in your calculator like this. So the sine of 1 minus 1, no, just divided by 1 squared, that's just going to be divided by 1. So take a look, we've got negative 1.5853, negative 1.5852. So even with only 3 terms, our fifth degree of Taylor polynomial gave us a pretty good approximation for the actual value of the function. And of course, the more terms you use, the higher the degree of Taylor polynomial, the more accurate it's going to be. So that's just to give you an idea of how these Taylor polynomials can be good approximations. But what if we wanted to know, and we didn't have a graphing calculator, what if we wanted to know what's the most we could be off by? Is this an acceptable approximation, or do we need to be more accurate? So in order to determine the maximum error of this estimate, we just saw how much it was off by, but if we didn't have our calculator to figure that out, that's where we go back to this remainder error for alternating series. So let's see what this says. It says when a Taylor polynomial is used to approximate a function, how can you determine how accurate the Taylor polynomial is when approximating the function? So for an alternating series that converges, this R, so n, here notice this is a Taylor polynomial, it ends right here, of nth degree, and whatever terms we don't end up using, R sub n, that represents the remainder. So really that's how much we're off by. That's why it's called the remainder or sometimes the error. All the terms we didn't use represent how much we're off by if it had gone on forever. So what this is saying is that remainder error, right here. Okay. Let's look at the notation here. This S, just like it does for a geometric series, represents the sum of the infinite series, of the infinite Taylor series, if you did use all the terms. And S sub n represents the sum of the Taylor polynomial. Of nth degree. So by subtracting those, we're saying, well, this is the actual sum, this is what our sum was with the Taylor polynomial. Subtract them, that tells you how much you're off by, or what the remainder error is. Notice it's an absolute value sign, so we're always considering the error as a positive value. And what it's saying is that error is always going to be less than this expression right here. Well, this is actually a lot less complicated than it looks here. It's a little hard to read, but those are plus signs there, and plus 1, and plus 1. And then plus 1 there. So if the last term we use has a degree n, what this expression here represents, n plus 1, is the next derivative, the next exponent, and the next factorial. So it's basically representing the next term, or in this case the first term, not used by the Taylor polynomial. So to see why that would represent the most we could be off by, it's going to be our error is going to be less than that, is when you have an alternating series. So I'll show you a simple alternating series that's geometric here. So if we had multiplying by negative 1/2, 4, negative 2, positive 1, negative 1/2, positive 1/4, negative 1/8. Let's say we just used, and the Taylor polynomial just gave us these terms, those first 4 terms. What this is saying is the most we could be off by, it's always going to be less than this next term that we didn't use. In this case, the first term we didn't use was 1/4. That's what this represents right here. And you can see why that is, because as we keep multiplying by negative 1/2, the terms get smaller and smaller, and they're alternating. So there's no way it's going to be off by more than 1/4, because the next one's negative 1/8, the next one's positive. You can see those positive and negatives start to partially cancel each other out there. So what we're going to be off by is guaranteed to be less than 1/4 here, if we were to use just those terms for this series. So that's the idea. Now it says plus 1 here. A lot of times it will be the next power, but it's not always going to be. It's the next term, because sometimes we have terms that are 0, that are wiped out, and that's obviously not going to tell you what you're off by. So it's the next term in the series that you didn't use right after you stop your Taylor polynomial based on the degree. So let's see how that works for this one. Well, if we had kept going here, if we hadn't stopped with a 5th degree Taylor polynomial, then right here, that next term would have been positive x to the 9th over 9 factorial. Right? But then it still would have been divided by x squared, right? So it actually would have ended up being x to the 7th over 9 factorial. And then to figure out how much we're off by, in this case it's just seeing what that value is by plugging in our specific x value of 1. So that'd be 1 to the 7th over 9 factorial. Wait, 1 to the 7th is just 1. Now if you have 9 factorial, that's going to be a pretty large number, so you can just leave it 1 over 9 factorial instead of working out what it is. So the way this is usually written is the absolute value of the actual sum minus the sum of our 5th degree Taylor polynomial. The maximum error that this is off by is going to always be less than the next term we didn't use in our series, in our Taylor polynomial. So 1 over 9 factorial, which is pretty small. So even with these, as we saw with the calculator, even just using these first 3 terms of the Taylor series to create our Taylor polynomial, it gave us a very good approximation, which shows you some of the power of these Taylor series. So this is another way of saying this is the maximum error. It's just usually written like this, is less than 1 over 9 factorial. Okay, let's look at the next example now. So this one, the function g has derivatives of all orders, and g of x is e to the x minus 1 plus 1. And this time it says use the 3rd degree Taylor polynomial for g about x equals 1. So this one's not Maclaurin because it's not about x equals 0, to estimate the value of g of 3. Okay. So let's first focus on getting the 3rd degree Taylor polynomial. So again, it's much easier if you have the e to the x one memorized. So remember, e to the x, it's not alternating. It's got all the positive terms. You can look back here real quick to see what it is. It's like having sine and cosine, because you use both the odd and even exponents, and they're all positive instead of alternating, like sine and cosine alternate. So normally it start off with 1, and it still does start off with 1, plus, normally it would just be x, but here notice instead of x we've got x minus 1. So wherever there's an x, we're going to substitute an x minus 1, so it'll be x minus 1 to the first, plus x minus 1 squared over 2 factorial, plus x minus 1 cubed over 3 factorial. Well, how do we know how far to go? It tells us this is a 3rd degree. And notice this plus 1, that's not going to affect our x's at all. So that's where we can stop for our 3rd degree Taylor polynomial. And then we can put plus 1. And notice if we add the 1 with the 1 at the end, that gives us 2. And then, oops, let me just make room for, I forgot to write, this is going to be t sub 3, 3rd degree Taylor polynomial of x, would be 1 plus 1, 2, plus x minus 1 plus x minus 1 squared over 2 factorial, plus x minus 1 cubed over 3 factorial. There's our 3rd degree Taylor polynomial. So about x equals 1, we can see it's x minus 1s here instead of just x's. So that's the first thing we have to find. And then it asks us to use that to estimate the value of g of 3. So we just substitute 3 in for x to see what our Taylor polynomial gives us. So if we substitute in 3, that's 2 plus 3 minus 1 plus 3 minus 1 squared over 2 factorial, or just 2, plus 3 minus 1 cubed over 3 factorial is 3 times 2. So then if we keep simplifying that, that's 2 plus 3 minus 1 is 2 plus 3 minus 1 is 2 squared is 4, divided by 2 is 2. So it looks like all the terms are 2 until we get to this 4th term. That's 2 cubed, which is 8, over 6 reduces to 4/3. So here, if you have your terms and don't have a huge denominator like the last one, let's go ahead and simplify that to make it easier to tell what our approximation is. That's 6 plus 4/3, and 6 is the same as 18/3 plus 4/3. So we get our approximation of using our Taylor polynomial at 3 is 18 plus 4, 22/3. Notice on this one, we're not asked about the maximum error because we can't use that same formula because this series, notice, is not alternating. This not alternating. There's other ways we can tell the error, but not using the alternating series error test because it's not an alternating series. All right, let's take a look at another one that is, though. Again, h has derivatives of all orders. H x is x squared times cosine x. So again, if you try to do this the long way, the first derivative, you'd already have to use the product rule. This could take a while to get this 6-degree Taylor polynomial here. So thankfully, we don't have to do that if you have cosine of x memorized. So 6th degree, we've got x squared on the outside times, remember cosine, if you think about the graph as an even graph that's alternating between positive and negative values, so that can make it easier to memorize. So it's got all the even exponents, starting with x to the 0, but that's just 1. Then it alternates, that's positive, so then negative, the next even exponent, x squared over 2 factorial, then positive, next even exponent, x to the 4th over 4 factorial. Now normally to get a 6-degree Taylor polynomial, if it was just cosine x, I would go one more term and put minus x to the 6th over 6 factorial. However, because we've got this x squared in front, notice x squared times x to the 4th, that's already going to make it x to the 6th, so we can stop right there. So our 6-degree Taylor polynomial, x squared times 1 is x squared, minus x squared times x squared over 2 factorial is x to the 4th over, you could write 2 factorial, that's really just 2, plus x squared times x to the 4th is x to the 6th over 4 factorial is 4 times 3 times 2, that's 12 times 2 is 24. And that's it. There's our 6-degree Taylor polynomial. And now we're going to use that to estimate the value of h of -1. So let's substitute in -1, see what our Taylor polynomial gives us. Well, that's going to be -1 squared minus -1 to the 4th over 2 plus -1 to the 6th over 24. All right, so we just have to simplify this now. So -1 squared is 1, minus -1 to the 4th is 1, so that's 1/2, plus -1 to the 6th, another even exponent is 1 over 24. And this one's not too bad, so let's go ahead and get a common number so we can simplify this. First, notice you have 1 minus 1/2, that's 1/2, plus 1 over 24. But 1/2 is the same as 12 over 24, plus 1 over 24. So that gives us our approximation of using the 6-degree Taylor polynomial is 13 over 24. And notice this one actually is an alternating series, so it does ask us to find the maximum error of this estimate. Okay, so for the maximum error, remember, since it's an alternating series, and we would use the next term that we didn't use in the 6-degree Taylor polynomial. So notice the term that would have come right here after that, x to the 4th over 4 factorial, since it was positive, since all would be negative, x to the 6th over 6 factorial. But then don't forget, that would have been multiplied by x squared. So that would have actually been negative x to the 8th over 6 factorial. Okay. And then if we substitute in -1 there, we can find our maximum error. That would be negative, and then -1 to the 8th over 6 factorial. So that's -1 to the 8th is 1 over. Now you could leave it 6 factorial, or if you wanted to work it out, 6, 5, 4, 3, 2, 1. It's not that bad. That's 20 right there. Times, that's 6 times 6, 12. So 12 times 20 is, 2 times 12 is 24, so 240. Now notice it's negative here, but the error is always considered what it's off by is a positive with those opposite value signs. So when we say that the actual sum using the Taylor series minus the sum using our 6th degree Taylor polynomial is going to be less than, that's the absolute value. If you leave the negative, there's no way an absolute value can be less than a negative. It doesn't make sense. So it's going to be less than 1 over 240. We're going to be off by less than that. So the maximum error is what this is saying. This is the standard way of writing it, is less than that. So again, even with just 3 terms here, we're not off by a lot, right? The error is going to be, most we can off by, it's going to be 1 over 240. It's going to be less than that. All right, now let's take a look at some that are a little bit different, where we're just focusing rather on the polynomial on a specific term of the polynomial instead of the whole thing. So it says let p of x be the 4th degree Taylor polynomial. You can see it's 4th degree because the highest exponent is 4, about x equals 0. So this one's actually a Maclaurin series as well. And it says based on that, what's the value of f triple prime of 0? Well, the third derivative would go with an exponent of 3. So if we write down just the pattern for the Maclaurin series, it would be f triple prime of 0, x to the third over 3 factorial. But we know that the term with x cubed is 8x cubed, so this must equal 8x cubed. So really they both have x cubed, so what has to be equal is the coefficients. This f triple prime of 0 over 3 factorial would have to equal this coefficient 8. So we'd have f triple prime of 0 over 3 factorial is just 3 times 2, or 6, equals 8. So then to solve for the third derivative at 0 of the function, you just multiply both sides by 6, giving you that f triple prime of 0 would have to equal 8 times 6, 48. So here we're just focusing on one specific term to find the value of the derivative. Similar thing on this one, it just is a 7th degree Taylor polynomial. And it's about x equals 2. So it's not Maclaurin. You can see that by the x minus 2's there. And it's 7th degree because the highest exponent is 7. However, what we're looking to find is the value of the 5th derivative of the function at 2. So again, following that pattern for the Taylor series, just like the Maclaurin series, the only difference is 2 here instead of 0. That would go, and it would go with x minus 2 to the 5th power over 5 factorial. But if we look at our series, our Taylor polynomial, you can see the one with an exponent of 5 is right here. So this would have to equal 20 x minus 2 to the 5th. Again, they both have x minus 2 to the 5th, so what has to be equal are the coefficients. This 5th derivative of 2 over 5 factorial would have to equal 20. So we have the 5th derivative of 2 over, let's see, 5 factorial, 5 times 4 times 3 times 2. That's 20 times 6, so 120 would have to equal 20. So then to solve for that 5th derivative, multiply both sides by 120. So the 5th derivative at 2 would have to equal 12 times 2 is 24, and then add the 2 zeros. So it'd have to equal 2,400 in order for it to give you 20 there. So those are focusing on one specific term of the Taylor polynomial. And let's look at one more, a little bit different, where they tell you a function has derivatives of all orders at x equals 0, and let p sub n, so it really could use other letters for polynomial or t, but this n, notice, denotes the nth degree Taylor polynomial about x equals 0. So for part A, it says it's known that f of 0 is negative 2, and p sub 1 of 2 is negative 3. And based on that, we're trying to find, well, what's f prime of 0? So starting this one off, it may not be obvious how we're going to use that information to help us find f prime of 0. So the clue on where to start is this point we're given right here. This represents n is the nth degree Taylor polynomial. So this is the 1st degree Taylor polynomial. So let's try to write down the pattern for the 1st degree Taylor polynomial. So I'll write p sub 1 of x. because in order to utilize this information, we have to know what the first degree Taylor polynomial is, right? So that's our clue from right there. So let's follow the pattern. And sometimes when you're writing these out, it's helpful to write even the parts that aren't going to show up, just so you can develop the pattern. So the first one is going to be the zeroth derivative of 0, so f of 0, x to the 0 over 0 factorial. Plus, then it's going to be the first derivative, f prime of 0, x to the first over 1 factorial. And because it's a first degree Taylor polynomial, we're going to stop right there with the second term because it already has a degree of 1 right there. So now, let's see if we know anything we can substitute in here. So p sub 1 of x, well, we know f of 0 is negative 2 from right here. X to the 0 is 1, 0 factorial is 1, so that's just going to be negative 2. And we don't know f prime of 0, so that's what we're looking for. F prime of 0 divided by 1 is just f prime of 0 times x. So the first is just x. So that's getting us a little bit somewhere. And now, notice this is really just a point on our first derivative. Sorry, not first derivative. Point on our first degree Taylor polynomial. So now, this is saying the first degree Taylor polynomial when x is 2 equals negative 3. So this is like our y here. So we know this equals negative 3 when x is 2. And notice now we have an equation we can use to solve for f prime of 0, which is what we're looking for in the first place. So to solve that, you would just first add the 2. I'll move it over here. And then negative 3 plus 2 is negative 1 equals, this is just 2 times f prime of 0. Then last step to solve for f prime of 0, just divide by the 2. I'll just flip it around, so we get f prime of 0 equals negative 1/2. So sometimes you just have to start with what you can, and then as you go through the process, you'll kind of discover as you go how to figure out what f prime of 0 actually would have to be. All right, now let's take a look at part B. It says it's known that f double prime of 0 is 1, the second derivative is 0, and f triple prime of 0 is 2. Find p sub 3 of x. Remember, that represents the nth degree Taylor polynomial. So we want to find the third degree Taylor polynomial. All right, so let's start off p sub 3 of x. Now, the nice thing is part A helps us out a little bit. There's no need to go through these again because we already figured out what they are, right? So we know the first term is negative 2. We just have to go a little further. We know the second term is, well, it was f prime of 0x, but we just figured out f prime of 0 is negative 1/2, so that's going to be negative 1/2 x. So no need to find those again. But now we have to follow the pattern. So after f prime of 0, x to the first over 1 factorial, the next term after that would be plus f double prime of 0, x to the second over 2 factorial. And then the term after that, for this third degree, so we've got to keep going, would be f triple prime of 0, x to the third over 3 factorial. So we just have to simplify those. So the third degree Taylor polynomial is going to be negative 2 minus 1/2 x. And notice we're told f double prime of 0 is 1. So that's just going to be 1 right there, divided by 2 factorial is 2, so that's just going to be plus 1/2 x squared. And we're told f triple prime of 0 is 2, and 3 factorial is 3 times 2. So you can see, or 6, you can see the 2's reduce out, leaving you with just 1/3. And that's plus 1/3 x cubed. So then there's, we stop there because that's our third degree Taylor polynomial, which is what it asks us to find, p sub 3 of x. And the most challenging part of this one is part C. You just have to read it carefully here. Now it's introducing another different function h, which wasn't in the problem before. Before it was just the function f. And h is defined so that h prime of x is f of 3x. And we also know h of 0 is 5. So we want the third degree Taylor polynomial for h about x equals 0. So think You might think, well, we already found the third degree Taylor polynomial in part B, didn't we? But notice, that was the Taylor polynomial for f. This one's the Taylor polynomial for h. So let's follow that same pattern here. So we'll write, in this case, it doesn't tell us what to call it. Since these were already called p sub whatever, 3 or p sub 1, I'll just use t for Taylor polynomial. So t sub 3 for the third degree Taylor polynomial for h of x. Let's follow the pattern. The first term would be h of 0, the 0th derivative at 0, x to the 0 over 0 factorial, plus the first derivative, h prime of 0, x to the first over 1 factorial, plus h double prime of 0, x squared over 2 factorial, plus h triple prime of 0, x cubed over 3 factorial. Stop right there. There's our third degree Taylor polynomial. Let's see if there's anything we know right now. Well, we do know h of 0 right here is 5. X to the 0 is 1, 0 factorial is 1, so we actually know our first term of our third degree Taylor polynomial for h would just be 5. Next, we need to know h prime of 0 to get our second term, right? But we have h prime of x, so if we just substitute in 0 there, h prime of 0 would be f of 3 times 0 is just 0. So that's equal to f of 0. Well, f of 0. What's f of 0? Didn't we already find that? Or actually, it gave it to us right here. F of 0 is negative 2. So we know that's negative 2. So this is going to be negative 2 right here times x. So 1 factorial is just 1, so that's going to be negative 2x. There's our second term of our third degree Taylor polynomial. But now we need h double prime of 0. We don't have h double prime yet. So let's go from here and find h double prime. So h double prime of x notice it's just in general terms here, and you would just use the chain rule here because we have a function inside. So start with the outside. The derivative of f you'd write as f prime of 3x, right? Leaving the function inside the same, but using the chain rule, you'd have to multiply by the derivative of the inside. The derivative of 3x is 3. So it'd be 3 times that. And then if we plug in, substitute in 0, h double prime of 0 is going to be 3 times f prime. 0 times 3 is just 0. Now let's see, do we know what f prime of 0 is? I think we do. 3 times f prime of 0, remember we found in part A, was negative 1/2. Giving you negative 3/2. So this would be negative 3/2 x squared. And then finally, we need h triple prime of 0. Before we can find h triple prime of 0, we need h triple prime of x, the third derivative. So if we go from our second derivative here, h triple prime of x would be, well, the derivative of the outside would be f double prime of 3x. But again, using the chain rule on the 3x, we'd have to multiply by 3. And there's already a 3 out there, so 3 times that 3 would give you 9. And then if we substitute in 0, so what we need right here, h triple prime of 0 would be 9 times f double prime. 0 times 3 is just 0. Well, do we know f double prime of 0? That'd be 9 times, well, if we look back here, in part B it gave us f double prime of 0 is 1. So 9 times 1 gives you 9. So this one's 9 right here. Divided by 3 factorial, which is 3 times 2. So that's 9/6, which you can divide by 3. Reduces to 3/2. So this will be plus 3/2 x cubed. And there would be our third degree, actually Taylor polynomial, except I just noticed I made a mistake. I apologize. On this term right here, I forgot to divide by the 2 factorial. So negative 3/2 is this, h double prime 0. Divided by 2 factorial, that's like multiplying by 1/2. So this one's actually negative 3/4. Sorry about that. There we go. So now there's our third degree Taylor polynomial for h about x equals 0. And that concludes the notes for AP Calculus on the topic of Taylor polynomials, estimating using those Taylor polynomials, and finding the remainder error for alternating series.